a pragmatic approach, leveraging portable stimulus from Subsystem to SoC level and SoC emulation. The growing complexity of SoCs these days, early time to market, poses a great challenge for verification closure. This paper targets various levels of verification closure from modules to SoC, with the motivation to adhere portable stimulus-based approach, emphasize developing C-based stimulus from the beginning, and to reduce the time to market. As this paper demonstrates, leveraging C-test and the test bench allows infrastructure from a Subsystem to SoC simulation to SoC emulation to GLS closure. Considering the requirement of reusability and portability and the interoperability, the infrastructure is developed around the TLM 2.0 generic payload for all communication interfaces. This paper demonstrates the advantage of fast simulation as well as SV, power constraint randomization, UVM sequence layering, and ease of the use, and all this encapsulated in C wrapper used via DPI function calls to reuse at SoC. Various modeling and infrastructure challenges like reset, interrupt, and etc. are addressed, and demonstrating the huge advantage of lightweight and high-speed architecture. Key of the test bench architecture ensures that older infrastructure can be used the same way for native UVM verification, UVM sequence-based verification. Keyword Introduction. There has been a significant work done which proposes sub-level verification leveraging to SoC, posing enormous advantages like portable stimulus, early time to market, faster simulation, faster development, and of debugging cycles. Porting of test cases from Subsystem to SoC simulation to emulation is always challenging. This methodology helps in developing C-based stimulus right from the beginning at the Subsystem with fast development cycles. This paper aims further to demonstrate a working solution for the same exploring TLM 2.0 GP for all interfaces communications, making reusable, interoperable, and protocol-dependent test sequence, also covering various problems faced during the sequence and solution learnings. Emphasis is further laid on enabling the verification scalability to SoC emulation level, and shown in Figure 1. Below the such that the test cases infrastructure created for subsystem level can be easily ported to SoC level, and then leveraging it further to an emulation, expanding the number of packets and data. Figure 1 is the execution at subsystem level. The various techniques like switching off and diode clocks, reducing the activity, putting cores to sleep mode and back has been discussed well. This paper further leverages creating the subsystem approach to achieve the same as well. Further, the subsystem-based environment using the UVM and SV-based transactors, which are not only faster, minimum 3 times faster than core-based on various experiments, but quite simpler to implement update. There are various approaches based on creating the virtual platform, which has a processor's model encapsulated in VAA layer, using C models as core layer and Verilog wrapper. Considering the advantage of UVM-based transactors, approach has been established with the generic interrupt and reset layer, which is simple implemented as faster as well. And developing the C test at a much faster rate as subsystem can be directly ported to SoC simulation as well as the SoC emulation. And enhanced advantage of DPIs is for C and DSV dynamic communication allows users to simulate the changes in code without compiling the bench. This paper aims to demonstrate an easier and proven way to meet the goal for porting the stimulus from subsystem to SoC simulation to SoC emulation. 2. Infrastructure details. A. Subsystem infrastructures. The infrastructures used to model the verification test bench at subsystem level uses SB UVM-based VIPs, which are wrapped in C-BFM infrastructure using TLM2 GP port and DPIs for exchanging cross-language function calls. Figure 2 shows the subsystem test bench architecture, while execution core is the UVM driver at subsystem level, which has been replaced as a rear RTL core at SoC. Figure 2. Subsystem test bench architecture. Further, Figure 3 shows the stimulus execution at subsystem, while Figure 4 at SoC level. The Figure 3 execution at the subsystem level. The same test which has been developed at the subsystem level will be directly reused at SoC. The set of the overhead related to SoC, like boot or clock configuration, etc., has been taken care with the help of context mapping, where dummy functions implemented as subsystem are mapped to SoC APIs through context. Figure 4 is execution at SoC level. The B hooks for a subsystem at SoC. The various functions and callbacks are placed at C level for other preferred communications interfaces such as DMA and interrupt, etc. This will be served purpose via UVM driver at subsystem and RTL master at SoC. The C, a reusable, interoperable, protocol-independent test sequence. But the portable C test developed at a subsystem will be directly ported to SoC simulation and SoC emulation with the context-based pointer to SoC-specific execution, which at SoC will be mapped to SoC-specific functions. For example, the case of the boot, clock, reset, fault triggering, and clearing. Interoperable sequence used for the protocol driver protocol X using the TLM2 GP extensions for added on generic transfer sideband signals are compliant with the protocol driver Y without extensions. The protocol independent. Consider the case for register layer in UVM. If there is any change in protocol bus, only driver and adapter needs to be updated and the test sequences would not change. A similar is the case using TLM2 GP. The synchronicity, DPI compliance. Synchronicity, TLM 2.0 GP has GP-based non-blocking port communication. The C code updated needs not to compile as it dynamically linked via DPI cores. The infrastructure is direct compatible with the System C models due to use the TLM-based interfaces. Hence, can be used to develop the tested low-level drivers. The figure 5 is to demonstrate the communication flow between C and system value through DPI. Various processes are created to implement synchronicity. The figures 5, C and SV communication through DPI cores. The E, test execution flow. The SP word will initiate and test execution. Figure 6 depicts the test execution flow considering the implementation for register read-write APIs. The run_test API, which invoked the simulation further, transferred the control to sequence body, which has the implementation tasks to invoke the C-based test through DPI cores as well execution sequence in parallel. C-test further calls the instructions as in WR, RD APIs in C, which are calling the system value counterpart by generating trigger_event Based on the trigger event, the task waiting for the C trigger further gets unblocked and starting execution the command received from the C side. This communication is done by the non-blocking TLM port, which completes the loop implemented in DPI layers, and hence the one command processed, and now C jumps to the next command and instruction. The figure 6 is test execution flow. F. Reset handling. Reset handling has been done considering the reset of the various types SoC and DUT specific can be generated in simplicity, where DUT itself generates the reset, and explicitly, where the C is task triggered the reset, can be handled by this approach. A reset environment has been created which acts as a base layer for our connections and abstraction functions for execution. Depending upon the DUT and SoC requirements, the extended reset environment can be created and overridden. BFM, which can be called as C-BFM, C-based calls from a test to UVM-SV agent, has the agent event-based analysis port, which can be connected to reset environment monitor. This implementation makes sure to get sampled both implicit as well as explicit reset on the reset interface. Further at emulation, there are various techniques available for handling this reset, which are vendor-specific, but this paper demonstrates the base implementation, where the sticker-based driver has been created to insert reset the synthesizable driver. This synthesizable driver is parameterized to make sure the proper assert and deassert sequence to follow the as per the various types of reset: POR, functional reset, and disruptive reset. So now this is a figure 7 is reset handling. The G is vertically used. The Amber UVM-based BFM, which are in active mode at a subsystem level, are overridden via factory to be passive mode to monitor the protocol activity when used at SoC. This helps to monitor the protocol activity by leveraging the effort made at a subsystem. The H is interrupt modeling. Figure 7 is demonstrate the interrupt handling and execution, and 256 semaphore is implemented for various level and interrupt execution. All the processes are executed at level L1 level of semaphore. Once there is interrupt based on application, layer L1 is locked, making sure no new transaction will be processed, and a control moves to the L1 plus 1 next layer, where interrupt service routine will be served. Figure 8, interrupt execution diagram. The I is the C-BFM versus core for execution. This paper emphasizes on using UVM-based drivers through C-based DPI core, since with the experiment it has been observed that it's maximum 3 times faster than executing it through core, keeping the entire processing in the system Verilog, so the system Verilog powerful execution and simulated support can make the simulations faster. The GLS, gate level synthesis. The functional verification needs to sample one of the following: virtual SDF, which does not need testbench to drive input skews. The wrapper-based, the timing wrapper on TB to ensure the input skews as captures by BE data. The random deposit on the settable flops may use per script. All the netlist code will be compiled in parallel to the TB and merged at the end using super blocks, which save the time of GLS compilation. The result numbers using this approach a huge benefit of the fast GLS closure has been activated. K. The direct reuse of the test bench and the test cases in emulator. Front and RTL changes for emulation. Update memory view from the behavior to vendor specific. Update library cell view from behavior to RTL if any. The test bench changes for emulation. Replace the simulation clock generation logic with vendor tool clock generation method. Replace the reset generation logic from TCL-based approach. Execution flow. The test case C file is used to generate the hex file, which is loaded into the system memory at core serially boot vector address. Soon after, the core reads the first instruction from memory and starts executing via execution core as shown in Figure 9. Figure 9, C2 hex loading for emulator. C-test. GCC2 generate SREC, SREC to hex utility, hex load to SRAM. 3. Application. The stimulus creation that can be reused in SoC level test bench. The L-based and M-based verification. Level verification, special purpose RTL simulation. For example, to generate power analysis VCD. Directly use of the test bench and test cases in emulator. DFT verification. Section 4 is summary. The test bench architecture makes sure that it can be used seamlessly for native UVM verification. There is no need to have a separate UVM test bench for UVM sequence-based verification. The RT compilation simulations much faster due to the smaller sized database in fast UVM-based driver, hence the fast test case developed leading early verification closure. Synthesized value-based slave memory is used, which is the portability to SoC emulation, provide interoperable and protocol independent implementation, sense communication port to TLM 2.0 GP compliance. The powerful system value constraint resolver, UVM sequence layering, and case of the using assist in the early verification closure. The SoC independent test development, that is, when the subsystem has not been integrated into SoC. The TLM 2.0 compliance test bench can easily plug with the system C host for early low-level driver development. GLS faster a long time and can be run independent of the SoC. Acknowledge. Okay. The references are good. Today I read this paper is a pragmatic application leveraging portable stimulus from Subsystem to SoC level and SoC emulation. The DBCon 2019, India. Thank you for your time and see you next time.